This is a surface in 3 dimensions. It's what you get from a function of 2 variables, the equivalent of plotting a graph. The most obvious features of this particular surface are the 2 humps, local maxima of the function. That's how you would probably make a casual description of the surface. But this surface also has 2 maxima. It's clearly not the same. The maxima are larger, and they're offset one against the other. And this surface, well, that's totally different. It has depressions as well as peaks. You'll be getting well acquainted with that last model during the course of this program. Having a model is a luxury when dealing with functions of 2 variables. Most often, you're given the expression, and you have to use all your mathematical skill to work just with the symbols. So let's start with the expression for this function. We'll be using partial differentiation as a tool to explore it. And because the peaks and troughs are such a useful way to picture a surface, we'll want to know where the maxima and minima are. And we'll want to be able to know that just from using the expression without looking at the model. Now that's a tall order. So let's forget the model and start with the expression. You'll see that partial differentiation gives you a systematic tool for dealing with this. But before we use it, and as a way of familiarizing ourselves with the function, let's see how much David can discover just from using native wit.
Well, it's not all native wit. I'll be using the power of a small computer here to help me. But what I won't be doing just yet is using partial differentiation. That comes later. Our function f is a product of 2 terms, and so f vanishes when either of them is 0. The first term, xy, is 0, either when x is 0 or when y is 0. In other words, f is 0 on each of the x and y axes, along these 2 lines. F is also 0 when x squared plus y squared equals 1. Now, x squared plus y squared equals 1 is a circle, center the origin, and radius 1. So our function vanishes on this circle here. Now, what about the other regions in the plane where our function is non-zero? Well, let's look in the first quadrant. There, x, y are both positive. Now, in the first quarter circle, x squared plus y squared is less than 1, so at our second bracket, 1 minus x squared minus y squared is positive, and so our function f is positive. On the other hand, in the first quadrant outside the quarter circle, x squared plus y squared is greater than 1, and so our bracket is negative, and our function is negative. In the same way, we can tell what the signs are of f in each of the other regions in the plane. Minus, plus, minus, plus, minus, and plus. Now, even just this crude technique is beginning to give me some picture of the function. For example, in the first quarter circle, the function is 0 on each of the 3 parts of the boundary and is positive inside. So somewhere inside the quarter circle, the function must have a maximum. And in each of the other quarter circles, the function will have either a maximum or a minimum. But even though I've been able to pin down some of the maxima and minima in this way, I still don't have any idea of the shape of the surface. I can get some information on that, however, in this way. Suppose I want to know what the surface looks like along this line, say. Well, that line corresponds to a fixed value of y. A little below minus 1, say y is minus 1.15. If I look at the expression for f, when y takes this fixed value, I get a function of x, and I can plot it, or I can ask the computer to plot it, and I get this curve. You see that it's negative on the left, 0 at the origin, and positive on the right. And of course, I can do this for any section that I wish.
So David's method found roughly where the maxima and minima were. And his method also gives us a clue as to how to proceed, by using sections. See, here, at the end of the model, is exactly the curve that David got. a cubic curve, varying x for a fixed value of y. Well, this model was built using sections. And you can see that for each of these fixed values of y, we get a different curve. Each one is a cubic curve, and each one a function of x alone, because to get each section, we gave y a constant value. Now, we want a systematic method of finding maxima and minima. In this case, we were lucky. We could tell a lot about this function just by using native width, but that won't work every time. What will work is the idea of section functions. So, to begin our systematic hunt for the maxima and minima of this model, we want to take two ideas with us. First, that the model is built up of sections, each one corresponding to a fixed value of y. And second, that although we've built this model by slicing in this direction, we could equally well have sliced in this direction.
So how do we use those ideas? Let's take a look again at some more computer-plotted sections. This is the one we had before, for y is minus 1.15. Now let's increase the value of y continuously through 0. When y is minus 1, the curve has a horizontal point of inflection at the origin. When y is minus 0.5, the curve has a maximum on the left and a minimum on the right. Now when y is 0, the function f is identically 0, and so the curve is a horizontal line. When y is plus 0.5, the curve has a minimum on the left and a maximum on the right. Now that's the maximum that we're going to be interested in. And when y is plus 1, the curve again has a horizontal point of inflection at the origin. But we seem to have passed the interesting parts of the curve. Let's look at that again. But this time, we'll change the value of y continuously so that we run across the surface smoothly. We'll do that again. This time, concentrate on the maximum that forms on the right. We get a maximum as soon as y passes 0. From here on, until y is plus 1, the section function has a hump. Watch that hump and note where it takes its highest value. To make it easier, let's use the computer to record the highest value in that area. And now, let's freeze the section function that gives us that maximum. So now, I've pinned down something of importance. Lots of the section functions had maxima, but this one had the biggest. And now it's time to use our second idea and see what slicing in the other direction gives us.
Here is another model showing just two sections. This section is the one David found, and it has a maximum value here. Now, if we'd sliced in the other direction, this is the section you'd get through David's maximum. You can see that for this surface, there's a local maximum on the second section at the same point. In other words, both cross-sections have a local maximum here. Now you'll see that that seems to locate a maximum of the surface. Certainly, this seems to be a hump, even though most of the model is missing. But we can't be sure, just on the information we have, that the surface doesn't rise up here. But anyway, that's for this model. We want to be able to find maxima for any function without going to the bother of computer plotting of sections and building models. So let's look instead at the definition of a local maximum. At a local maximum of the surface, the value of the function at the maximum must be greater than the value of the function for any point close to the maximum. So if this point is a maximum of the surface, these two sections have to simultaneously have their own maxima. But just saying that doesn't say anything about what happens in these other directions. The surface could come up here, and then it wouldn't be a maximum. So the condition that the sections in these directions have maxima is necessary. Without it, we certainly don't get a maximum. But it's not sufficient by itself, because it doesn't guarantee a maximum. Now the next step is rather surprising. You might think that you have to develop a technique for looking at sections in all directions, but we don't need to do that. What we'll do is simply to look for extrema of the sections in these two directions. As well as the maximum we're after, we'll get lots of other interesting behavior as well. In fact, we'll find the stationary points of the surface, which include the maxima and minima, and use the techniques of partial differentiation in the rest of the unit to sort out which is which. So to find out exactly where this maximum is located, let's look for two simultaneous maxima of these two sections.
And to do that, we need partial differentiation. Remember that earlier I looked at this section. Now, I could do that for any section I chose. And if I knew which section passed through the maximum, I could do it for that section and find out where in the section the maximum came. But I don't know the y value of that section. That's what I'm trying to find. So for the moment, we won't give it a value. We'll just call it y. And you'll have to remember that although y is unknown at the moment, it's a fixed value, so it's just a constant in this expression. You've seen in the text that partial df by dx is the derivative we get by treating y as a constant. To work out the derivative of f, I'll first of all multiply out f to get this expression. If I now differentiate that with respect to x, I get this expression for partial df by dx. Just looked at as a function of x, we have to remember that y has a fixed value, the value we're searching for. And at our maximum, our partial derivative is equal to 0. And to pin down the x value in the same way, we calculate partial df by dy and set that too equal to 0.
Well, that's the way of catching our maximum. Treat the function as if only x varied, and use the rules of ordinary differentiation in one direction to find the partial derivative of f with respect to x. Now that's a function of x and y. And the same technique in the other direction will give us another function of x and y. Two equations. Solve them simultaneously for x and y, and we get the coordinates of the maximum. Well, partly true. Just finding where partial df by dx is 0 and partial df by dy is 0 will certainly find us the maximum we're looking for, but it will do a lot more besides. The maxima and minima are just particular cases of stationary points, points where partial df by dx is 0 and partial df by dy is 0. And using this technique, we'll just find us the stationary points. But before we go on, let's just be sure that we've convinced ourselves that this technique really works by looking at it another way, a more geometric way. A maximum on our surface, remember, has to have a value greater than the values around it. So this plane here, the tangent plane, has to lie above the surface, and the tangent plane has to be horizontal. Can we convince ourselves that searching for a horizontal tangent plane is the same thing as searching for two maxima on the section functions? At a maximum on a section function, the tangent line is horizontal. But on the surface, at every point, there are an infinite number of tangents. Two in particular interest us. One in the direction of these sections, the other at right angles. As we move around the function, these two tangents change independently. Let's concentrate on our maximum. The two tangent lines define a tangent plane. As our point of interest moves over the surface, the tangent plane changes. At our maximum, the tangent plane is horizontal, regardless of which direction we approach the maximum from. We search for the maximum just by using the tangent lines along the sections. Along this section, the tangent line is horizontal at the maximum. And that's true along this section too. So what about the tangent plane? At every point along this section, there's a unique tangent plane. Here, this tangent line is horizontal, but the plane isn't. We haven't found the maximum. Searching along the correct section, we see that the tangent plane is horizontal. The tangent line is horizontal, and so is the plane, because the other tangent line is also horizontal. Whichever way we search, the tangent plane is only horizontal where both tangent lines are simultaneously horizontal. So that's it. Our strategy works. If we use partial differentiation to look for the stationary points, we'll find the maximum in among them. It only needs us to solve these two simultaneous equations, and we're there.
Right. This is where you'll really get your hands dirty. Partial differentiation tends to throw up expressions like these quite often. So much so that there's a tape section specifically designed to help you solve equations like these in the unit. But let me at least give you the flavour of the work to be done. Notice that the first equation has a common factor of y. So we can rewrite the first equation as y times a bracket equals 0. And the second equation, well, that has a common factor of x. So we can rewrite the second equation as x times another bracket equals 0. Now, what values of x and y satisfy this first equation? Well, either y is 0 or the bracket is 0. So there are two possible cases here that we must consider. And how do we satisfy the second equation? Well, either x is 0 or the bracket is 0 again. So there are another two possibilities that we must look at. Altogether, there are four possible cases. Let's look at the first one. Well, here x is 0 and y is 0, so 0, 0 must be a stationary point. Now, in the second case, x is 0, and substituting for x in the top equation, we have that 1 minus y squared must equal 0. In other words, y is plus or minus 1. This means that we have another two stationary points, 0, 1, and 0, minus 1. In just the same way, we can look at stationary points which occur in these other two cases, and we find another 6 stationary points altogether. So, if we put all of the cases together, we find that we get the following 9 stationary points.
So there are 9 solutions in all, and all of them are stationary points. Some of them are maxima, some minima, and some other interesting solutions besides. The text has a technique for sorting all of these out, but I can use David's native wit again to save time. David found 4 maxima and minima inside the circle. Among these solutions, there are 4 stationary points inside the circle, so I can classify these immediately. Well, what about these other 5 solutions? Let's take a look at this one. Now that's this point here on the model. The tangent line in this direction is horizontal, as it is all the way along this line, which is the y-axis. In this direction, the tangent line is horizontal too. But the behaviour around this point is rather complicated, and you'll see that we didn't get all the information from what we've done so far. It's not a local maximum. This point is above it, nor is it a local minimum. In fact, it's an example of what is known as a saddle point. And what's really interesting in looking at surfaces is the wide variety of behaviour like this that you can get near a stationary point. This surface is well behaved. It's got a maximum. In just the same way, this surface has a minimum. But here, this surface has a minimum in this direction, but in this direction there's a maximum. This is a saddle point, and you can see how it got its name. It's a rather exaggerated form of a horse's saddle. Here's another saddle. You couldn't sit on it. It's certainly a stationary point, but this time horizontal points of inflection, whichever way you approach the saddle. And finally, an even more complex saddle. You can see the need for a technique to sort out this behaviour. In this direction, and in this, there are maxima. You might carelessly think it's a maximum, but in this direction, and in this, there are minima. So if there's one important message to take from this program, it's that we really need the techniques for sorting out the behaviour of surfaces that you're just about to meet in the text. But let's just quickly review what we've done. We've been looking for a local maximum, and we've found it by partial differentiation. We looked at the partial derivatives of the function and solved these two equations. If we'd been searching for a local minimum, we could have found it the same way. Remember that solutions of this pair of simultaneous equations give us maxima, minima, or saddle points. Well, the details of telling for any given solution if it's a saddle, a simple one, or a complicated one, are in the rest of the unit.